Welcome, everyone. So today we'll continue talking about kinetics. So let's see here. Started talking about, we did the steady state approximation. Yeah, we should talk about what that was, right? We didn't do pre-equilibrium yet. I'm trying to remember what we did on Monday. I don't know, it's just 2 days ago. I should remember this. Did we talk about kind of rate determining step in pre-equilibrium approximation? Yes or no?
No.
That shakes no? Okay, no, okay. Yeah, so we did talk briefly about the steady state. I believe I did do that, right? So I'll just refresh our memory, right, just to make sure, right? The idea of the steady state approximation is to say this, right? That the change in concentration of your intermediate is, with respect to time, is equal to 0, right? That doesn't mean you don't have any intermediate concentration. It just means that it's relatively constant, right? And it's typically also very small and constant is the idea. Okay, it's a steady state approximation. Okay, and we can use that to solve potentially for rate laws like this, right? Okay, right, and here, right, you say our intermediate in this case is the oxygen atom, right? And so you'd say, you know, oh my gosh, dt, right, equals 0, which then would equal, right, then the question is, what is the change in concentration of O as a function of time? Well, we know O is being formed by this first reaction. I'm going to call it at a rate VA, right? Because O is being formed in that first equilibrium reaction in forward direction VA, right? It's being consumed in the reverse reaction V minus A. So the concentration is going to decrease at whatever rate that the reverse reaction in equilibrium is going, right? And then oxygen is also a reactant and is being consumed in the second reaction here. And so it's going to be minus VB, right? The rate in which that second reaction here is occurring, okay? And then we can just use the fact that these are elementary steps to write out the rate laws, right? So VA is just Ka times concentration of O3, right? You know, so on and so forth, right? V minus A is K minus A, O2, and VB would be concentration of O times concentration of O3 times KB, okay? And then you can use that to solve for the concentration of your intermediate O in terms of concentrations of O3 and O2, which are reactants and products in your mechanism, and those are things that we can measure typically and have concentrations that are not typically extremely small, like intermediates can be. Okay. So kind of questions about that. I know I didn't finish kind of writing things out here, but are there any kind of questions about the steady state approximation? All right. Again, hopefully, you know, a lot of things that we're going to kind of do and cover in this class, hopefully are review, though, you know, when you last took a physical chemistry course, it varies, right? Right, because again, since everyone in this class has a relatively different background and are in different labs and doing different things that often potentially aren't even much related with physical chemistry, right? And so, you know, we want to make sure the class is useful to you in the future and whatever those endeavors might be, right? And so, so again, hopefully,
yeah, it is answered that we need to.
Hopefully, some of this is a review and such, right? But if not, that's more than fine, right? That's why we're talking about it and doing it. Okay, so.
And
But if they're, oh, go ahead.
Maybe just to jump in really quick related to what you just said, I'm planning on sending out a quick survey just to get to know you guys a little bit better and what your backgrounds are and interests and what you hope to get out of this course. So I will post that in Canvas and you should get an email when it's ready, but just an FYI, since you were on the subject.
Yeah, no.
Different builds, we need to make sure that the firmware.
So, all right. Okay. Let me move on. Right. So there's another example here. You know, this is definitely a very complicated example, but another example here with kind of the final solution as to what this DHBRDT comes out to be. Now, Ka and Kb are some products and ratios of some of these rate constants, K1, K minus 1, K2, K3, and K4. But, you know, if you work things out, you can, you know, work out kind of what this final functional form is. But I'm always happy to go over that with anybody if they'd like to at some point outside of class. So, yeah, so that's the steady state approximation. The pre-equilibrium approximation is a little bit kind of simpler, more straightforward, and it is even taught in general chemistry. I teach this in general chemistry when I teach general chemistry. I don't teach them the steady state, but I do teach pre-equilibrium and rate determining step, right? And so, right, rate determining step, hopefully is something very familiar, right? You know, your reaction, the speed in which it occurs is given by the speed of the slowest step, right? So the slowest step determines how fast that reaction is going to occur. Okay, right. I often relate this, you know, in a large classroom with the idea of when you're running out of the classroom, right? Because the fire alarm went off, right? If there's 100 people in the classroom, right? The speed in which everyone gets outside the classroom is not how fast can they run to the door, but how fast can they get through that door, right? That second step of getting through the door is going to be the rate determining step, right? Because only so many people can fit through a door at a time, right? That's why you see, right, with people rushing out of a room, right? You know, this huge blob of people kind of circling around the exit, right? Because everyone can get to that spot very quickly. They just can't get through it very fast, right? So that's your rate determining step, and that determines how fast you get out of the room, right? And same thing with chemical reactions, right? If you have some step which has a high activation barrier compared to the other steps, typically that's going to be much slower than all other steps. So it's going to be a rate determining step. And so you'd say the rate of the reaction is just equal to the rate of this rate determining step, okay? This slow step, right? So if I had this mechanism, right, and I said that first, you know, so this is kind of the mechanism for, say, this reaction here, right? This energy profile, right? We have this mechanism, okay? And I say, okay, that first step is the slow step, okay? Well, given the fact that the first step is the slow step, right? And this is an elementary step, right? The rate law for this elementary step is just K1 times concentration of B times concentration of F. And because this is my slow step, my rate determining step, the rate of my overall reaction is equal to the rate of that first reaction, which is just K1 times B times F, right? And since B and F are reactants, right, we're done, right? We don't need to worry about anything else, right? That's our final rate law, and we're good to go. Okay. Now, often this rate determining step will be combined with what's referred to as the pre-equilibrium approximation, okay? Which is just basically stating, right, that if I have some slow step and right before that is a fast reaction that can go in either way, so an equilibrium reaction, right? So a reaction that can go fairly quickly in either direction, and it happens very quickly, right? Then the idea is that first reaction is always in equilibrium during the entire time your reaction is taking place, right? Because the idea is right, A forms I to establish equilibrium very quickly, and then that I is slowly being consumed to form P, but as I is being consumed, it's immediately getting replaced by the equilibrium reaction, and equilibrium is reestablished, right? So the concentrations of A and I and P can be changing over time, even if your reaction stays at equilibrium, right? Because again, equilibrium doesn't mean, right, that you know, a reaction at equilibrium doesn't have to be at a certain set of concentrations, right? It all depends on the ratio of concentrations of products over reactants, right? So as long as the ratio of I over A always equals the same value, I can increase A, I just got to also increase I, right? So yeah, so the pre-equilibrium approximation, right, just says that, hey, we're at equilibrium for that first reaction the entire time, right? And what that approximation does, it says, okay, well, since we're at equilibrium, okay, right, I know that I satisfy this equilibrium constant, right? The equilibrium constant for that first reaction is just the concentration of I divided by the concentration of A squared, right? And that happens to equal K1 divided by K minus 1, the rate constants. We had this kind of shown earlier in some slides when we talked about reactions, elementary reactions that are in equilibrium, right? And you get this relationship here by just the fact that it's set in the forward rate being the rate of A plus A forming I, has to equal the reverse rate, right? That's the definition of equilibrium in chemistry, right? Is that the forward rate equals the reverse rate. So A plus A forming I, it happens just as fast as I forming A plus A, right? When you set those two rates equal to each other and then plug in for what the rate laws are for those two rates, you get this formula down here, right? Right, this formula down here, which then you can happen to notice that I divided by the concentration of A squared is just the ratio that gives the equilibrium constant, right? And so, yeah, right. And so then I can use this to get rid of the intermediate from my, say, rate law, right? To get, say, this final rate law expression, K2, K1 over K minus 1 times concentration of A squared. Yeah. So often the pre-equilibrium approximation is a little bit of a simpler one, right? It just basically says your equilibrium constant valid because your reaction's always at equilibrium. So the equilibrium constant equaling those ratios of concentrations always holds true, and you can use that to substitute in your intermediate, or, for your intermediate concentrations, right? For this intermediate concentration, I can use the pre-equilibrium approximation to substitute in concentrations of reactants and products. Questions about the pre-equilibrium approximation?
I have one question. So, well, I have seen in many of these equilibrium equations that in the fastest step, we have two Ks, K1 and K, in this case, minus 1. Why we have two?
Why are there two?
Yes.
Yeah, so the question, right, why are there two Ks in this first step? The reason is because really I have two reactions here. I have the forward reaction A plus A forming I, and then I have a second reaction that is I forming A plus A, right? An equilibrium reaction has the forward and the reverse reaction. So K1 is the rate constant for the forward reaction, and K minus 1 is the rate constant for the reverse reaction, right? So I could have written this same mechanism as like, three lines, right? A plus A forming I, with K1 as the rate constant, I forming A plus A as K minus 1 as the rate constant, and then I forming P as with the K2 rate constant, right? But yeah, so often though that equilibrium reaction rate is just written like this, just so we can write it in one line, and then you put two rate constants here, one for the forward and one for the reverse. Great. Any other questions?
So I have a question about the both approximations. So when we apply the steady state and when we apply the pre-equilibrium approximation?
Yeah, so the steady state approximation basically is typically used in general if you're using any approximation. So the steady state is one that pops up in all sorts of places. You use steady state approximation for enzyme kinetics. We talked about that, right? You use steady state approximation for photochemistry kinetics. So the steady state approximation is something that, while is an approximation, is applicable enough to a variety of systems that typically that's kind of the go-to approximation if you're going to use one.
So you mean there will be no equilibrium in the steady state? Like every reaction moves toward the equilibrium. So in steady state approximation, the reactions that they are following are not going toward the equilibrium?
Yeah, so in steady state so let's say, right, I didn't know this was fast and this was slow, and I just had these reactions, right? The steady state approximation isn't, you know, it will, what it's saying, right, is that the concentration of I is relatively constant, right? Well, if the concentration of I is basically constant throughout the reaction, right, as I'm losing A, right, so as the concentration of A is decreasing, the concentration of I is staying the same. So there's no way I can maintain equilibrium. So definitely you can't have both things occurring. You can't have the equilibrium and the steady state kind of happening at the same time, if you will. Right. And so in terms of like, when do you need to know, right? If you're given a problem, you'd be told use the steady state approximation or use the pre-equilibrium approximation, right? In terms of like problems in this class, you'll just be told which approximation to use, right? If I were in lab, right, I would typically be trying to do some experiments to see if I have a rate determining step, right, in my mechanism, and you know, and then use that to help kind of figure out the rate law, and then potentially use steady state or something like that, you know, or pre-equilibrium if it makes sense based off of my mechanism, right? So you know, you need kind of more information about what's happening in lab to kind of decide which approximation seems more valid. But one thing we can show, I don't know if I have an example of this. Yeah, right. So this exact same example, you can compute using this, you know, the steady state or pre-equilibrium. And let's see here. I think I have this. Hold on, let me pull up something. Oops. I have the solutions to that. I typed that somewhere, I believe. Just give me just 1 second. I'm in the wrong spot. It's here. No, not quite the same reaction, but that's fine. Sorry, I had another class today and I did something somewhat similar. Oh, no, I can't do that. All right. I can do that. But so I will at least kind of show these slides just so you can kind of see the idea, the difference between them. So the reaction here in this problem, where do I go? Oh, yeah. So it's a similar type of system, right? Setup, right? You have we have a reaction and an equilibrium reaction, right? So it's not quite the exact same reaction as the O3 going to O2 plus O and O3 plus O going to 2O2. So it's not the same reaction, but the same rough mechanism, right? There's two kind of steps. The first step is the equilibrium step. Second step is you know, just unidirectional, right? And there's one intermediate. Okay. So given that kind of mechanism, you can go through and work out the rate laws using the steady state or pre-equilibrium approximation, okay? And you'll get these two answers here. So you'll get, you know, not you know, so nice, simple looking, right? A couple of Kc, Kds, and concentration A squared times B, and so on and so forth, okay? But one thing you might be able to kind of notice here is that the pre-equilibrium approximation is actually a simplified version of the steady state, right? The pre-equilibrium approximation, I assume Kc times concentration of A is extremely small compared to K minus D times concentration of D, right? So that this denominator just simplifies down to K minus D times concentration of D, right? And so the pre-equilibrium approximation actually, you can get typically from the steady state approximation, not guaranteed every time. It does depend on the mechanism, but for certain mechanisms, you can even kind of get the pre-equilibrium approximation by just making some simple approximations or assumptions. Okay, right? And that assumption, Kc times concentration of A being much smaller than K minus D times concentration of D. What that's getting at is Kc times concentration of A is related with the rate of that second step, and K minus D times concentration of D is related to the rate of the reverse step here, right? And so what that's saying is basically that this second step is extremely slow and the first step is very fast, right? Which is what the pre-equilibrium approximation says, is that this step is very slow and then the first step is very fast. And so you've established equilibrium in order to have, given that kind of set of rates. So you have a slow and a fast equilibrium, right? And so, yeah, so you can get that pre-equilibrium from kind of the steady state as well. So you could do the same type of thing here, work out the steady state approximation and the pre-equilibrium, and you'll see that they're very much related to each other for this simple mechanism. And the pre-equilibrium is actually just kind of an approximation of the steady state. So other questions? All right. So we're gonna not bother, since we're cutting off a little bit of what we're doing with the kinetics, we're not gonna kind of focus on this unimolecular kind of mechanism. It's called the Lindemann-Henschel-Wood mechanism. So, again, I believe I removed everything from kind of that second kinetics homework from this, right? And so, yeah, and let's talk about enzyme kinetics. We'll at least we'll talk about just the enzyme kinetics itself and the Michelson-Menten kind of mechanism plot. And then later, after photochemistry, I don't think we'll have time to get to it, but after we get to photochemistry, I do have things on here where we have enzyme kinetics with inhibitors. So I don't know if we'll get to that today, we'll see. But if you're interested in it, the things are worked out kind of in these slides and things like that. And I highly recommend you kind of look over this, and you're welcome to talk to me about it if you're kind of interested in kind of enzyme kinetics with inhibitors, right? Yeah, so let's go back to enzyme kinetics here. So, all right. Our typical mechanism for a simple enzyme reaction is as follows, right? You have an enzyme in solution, some sort of substrate in solution that can bind to that enzyme, and that will establish some type of equilibrium, or can establish an equilibrium, right? But that is an equilibrium type reaction, right? The substrate can bind to the enzyme and then it can unbind, right? It can attach and detach, right, from the enzyme. It's not permanently attached. And then when the substrate is bound to the enzyme, this enzyme can help that substrate undergo a reaction to form some product, and then it will release the product and you get the enzyme back, right? And so the enzyme here, right, is a catalyst for this mechanism, right? It helps the overall chemical reaction is just substrate going to product, right? And the enzyme here is a catalyst, okay? Often in this type of thing, right, the second reaction is a little bit slower. We don't need to assume that, but often it is, okay? And so the rate of formation of the product is related with the rate of the reaction, okay? Again, right, right, where this comes from, right, the rate of the reaction, V equaling KB times concentration of ES. This comes from the basic idea, right, that we define the rate of the reaction as the rate of formation of products or the rate of consumption of reactants divided by their stoichiometric coefficients. Here, my stoichiometric coefficient is 1, right? And so the rate of formation of my product is just given by the rate of this second reaction, which is just KB times concentration of ES. And so that equals the rate of my overall reaction. And so this is the rate law for my overall reaction, right? Now the problem is it's in terms of this enzyme substrate intermediate. And so we need to get rid of that, right? And so to do that, we're going to use the steady state approximation and say that the concentration of the enzyme substrate intermediate doesn't really change with time, right? And so that's our approximation. Say it's roughly constant with time, that concentration. Okay. Any questions about kind of the basic premise of what's going on in these enzyme reactions? Right. So right, in these enzyme reactions, right? Right, so we write out what that steady state approximation is, right? Enzyme substrate appears in the forward direction of this equilibrium reaction, the reverse direction of the equilibrium reaction, and the forward direction of this second reaction here, in which it's a reactant in two of those reactions, so it's got a minus sign, okay? And then, you know, it's a product in that first reaction, that forward direction. So it's you know, positive, right? And then it can just factor out the concentration of ES here, add all of that to the other side, and then divide out K minus A plus KB, right? To rearrange this equation here to get the concentration of ES is equal to Ka times E times S divided by K minus A plus KB. Okay. And so, you know, that's good. We have, right, what is the rate of our reaction in terms of concentration of enzyme and concentration of substrate, okay? But the problem is that's the concentration of free enzyme, right? How many enzymes are unbound, right? And depending on the ratio of substrate to enzyme, that number of free enzymes might be very small and might be very different from the initial amount, right? And that's not necessarily something that you can easily measure as the reaction is going, okay? And so that's something that we want to kind of get rid of the dependence on the concentration of free enzyme, but instead want it to be dependent upon the initial concentration of the enzyme, okay? And so we're going to take an extra step here, right, where we're going to use the fact that the total concentration of the enzyme, which is equal to the initial concentration, is just the concentration of the free enzyme plus the concentration of enzymes that are bound to substrate, right? Should make sense, right? My enzyme is either unbound or bound to a substrate, okay? And that concentration of those should add up to the initial concentration, okay? And so from last slide, we had, right, what is the concentration of my enzyme substrate in terms of enzyme and substrate? I'm going to rewrite this equation by solving for the concentration of enzyme, right? So I'm going to multiply K minus A plus KB onto the other side, and then we're going to divide Ka times S onto the other side to get this equation here, which I'm going to rewrite as Km times Es divided by S. Km is this Michelson-Menten constant. Okay, it's not quite an equilibrium constant. Okay, the equilibrium constant for the binding of the substrate with the enzyme is related with Ka over K minus A. Okay, but what this kind of tells you, right? So the denominator here is this rate constant is related with how fast the substrate binds to the enzyme and how strong, right? How fast and strongly does the substrate bind to the enzyme? And the numerator is the rate in which that substrate leaves, either as the substrate or as the product, okay? And so this Km, value of Km is related with kind of how strong your enzyme is bound to the substrate, okay? If Ka is very large and K minus A and Kb are very small, that means the substrate binds very rapidly to the enzyme, but doesn't really leave, which makes Km a very small number. And so when Km is very small, you have very strong binding affinity of your substrate to your enzyme, right? And if Km is very large, then it potentially has very weak binding affinity compared to how much it wants to be unbound, right? And that can be very important for an enzyme, right? You may or may not want a substrate to bind strongly or not, right? And that's something that often you have to monitor, control, or figure out. You know, if you're designing a substrate for an enzyme or wanting to design a catalyst, right? So say enzyme for a substrate. Anyways, right, so that's what Km is. And so I can plug this equation here, E equaling Km Es over S, into the above equation, E naught equaling E plus Es, right? So I can plug that in, okay? So I get Km times concentration of Es divided by S plus concentration of Es, right? I'm going to factor out that concentration of Es to get 1 plus Km over S. And then we can rearrange that, right, by dividing 1 plus Km over S on the other side, okay? And you get that the concentration of the enzyme bound to the substrate is equal to the initial enzyme concentration plus 1 times Km, this Michelson-Menten constant, divided by the concentration of your substrate. Okay. And so then the final rate, right, if we go back, right, the rate was just ES, concentration enzyme substrate times Kb. So the final rate is just Kb times that initial concentration of enzyme over 1 plus Km over S. Okay. Right. And this is often rewritten as such here. Okay. So the final rate is written often like this: Kb times S times E naught over S plus Km. Okay. Right. And so this is this rate law for this simple mechanism in terms of the initial enzyme concentration and the substrate concentration. Okay. And then this Michelson-Menten constant, which is K minus A plus Kb divided by Ka. And then this Kb rate constant here. Okay. And then you can see here that if you have low concentration of substrate versus high concentration of substrate, that this rate law can either be dependent upon the substrate concentration or completely independent and just depend upon how much enzyme do you have, right? So questions about this mechanism? Okay. The main difference in this mechanism than a lot of other ones that we've talked about that you'll do kind of practice with and things like that is kind of this step here of the fact that we want to not have the current concentration of enzyme, but instead the initial concentration of enzyme in our final rate law expression. And so we had to do some extra little steps in order to get there. Okay. All right. So we're going to kind of skip that example. And let's go on talking about photochemistry. I'll take a second to see if there were any other questions about kind of those enzyme kinetics. Okay. I'll at least quickly jump to inhibitors, just show you kind of the expression here, like for a certain type of inhibitor, how it changes. Okay, so before we had K times S times the initial concentration of enzyme, and then S plus Km, and then you get this extra term in the denominator that kind of appears. That can affect things. For an uninhibited inhibitor, or sorry, for a competitive inhibitor, which is what this is. And then there are other things for non-competitive and uncompetitive inhibitors. You can work things out. Okay. So, but again, if you're kind of interested more in this stuff, I'm happy to talk about it. Anytime, just send me a message and we can set up time to chat. So again, any questions about anything related with kinetics before we do this kind of discussion on photochemistry? And sometimes I feel like we're just jumping quickly through a lot of things here, and I don't want people to feel overwhelmed. You may or may not be, I don't know. But I don't want that feeling, so I'm happy to slow down, right? Take as much time as needed to talk about things or answer questions or examples or whatever.
So can you a little explain about the affinity of the substrate and enzyme toward the rate of the reaction? Like any relation between these two?
Yeah, so here I'll right, so Km, sorry, right, it was this K minus A plus KB over K. Okay, right, so that was the definition of Km, Ms. Nicholson mentioned constant, okay, which we know, if you look, right, K minus A and Kb, right, are for the reactions where the substrate leaves the enzyme, right? Right, K minus A is the substrate leaving the enzyme to form enzyme plus substrate, right? And then Kb is that rate constant for the reaction where you form the product, right? But again, if the substrate's leaving as a product or as a substrate, it doesn't matter, right? It's leaving the enzyme, right? So K minus A plus Kb is, you know, the sum of the rate constants, which is related with, right, kind of the rate, like how fast do I rid myself of this substrate, right, from my enzyme, right? And then
yeah, save money you have to buy.
is
Also get,
you know, related with how quickly the substrate binds with the enzyme, right? Ka times concentration of E times concentration of S, right, gives you the rate in which you form ES, right? And so Ka, that rate constant, is related with how quickly you form the enzyme substrate, and then K minus A plus Kb is related with how quickly you deform, right? You unform, or however you want to call it, right? The enzyme substrate to get the free enzyme back, right? And so, right, these rate constants, right, are related with how fast these reactions are, right? So if I have very fast binding, right, very large Ka compared to K minus A and Kb, right, this Km will be a small number, okay? Because I'll have a large number in the denominator and a smaller number up top, right? And that's indicating, right, that my substrate is binding to the enzyme very quickly, right? Okay, and that it's not really leaving the enzyme very fast, right? Which means that it's going to be strongly bound to the enzyme, right? Because it gets bound and it stays there, right? But if K minus A plus Kb is very large compared to Ka, right, such that Km is a large number, right, kind of the opposite extreme, right? So when Km is very small, that's indicating your substrate is strongly bound to the enzyme. When Km is very large, it's indicating that the substrate doesn't really bind strongly at all to the enzyme, right? That as soon as it binds, it's kind of kicked off, right? And likely it gets kicked off as substrate, not necessarily as product, right? But maybe it's an extremely fast reaction, right? And you kick it off as product very, very quickly, right? Could, okay. But yeah, but so you know, the smaller Km, the more strongly bound your substrate is. The larger Km, the more weakly bound that substrate ends up being. Any other questions about any of this enzyme kinetics, steady state, pre-equilibrium approximation? All right. There. Okay, so in photochemistry, we're going to be talking about kind of just the kinetics of photochemistry of molecules after they've been hit with light and gone into some excited state, right? With Kelly, you're going to be talking about spectroscopy and these excited states and selection rules and things like that, right? Here we're just going to use the fact that, hey, you know, the electronic states of your molecule have discrete energy levels, and you can go from one to the other by absorbing or emitting light, right? And let's talk about the kinetics of that process. Okay. So, sorry. Right. And so, if you recall, right, electrons have spin of +1/2 or -1/2, okay? The m sub s quantum number, okay? Now you can have, say, that +1/2 electron, right, that upspin electron in the same orbital as a downspin electron, and those guys are paired up, right? And if your entire molecule has orbitals with electrons all paired up, it's considered a closed shell species, and it's considered a singlet electronic state, because there's only one way you can put your electrons in these orbitals to pair them up to have the same number of up spins as you do down spins. Okay, so that's where this term singlet comes from. Okay, right, and so this is kind of a singlet energy state. This would be like a singlet ground state. Most molecules, especially organics, are singlet ground states. All of their electrons are paired up. They have an even number. They're just closed shell singlets. Very simple, very nice. Now you can have a different set of spins where, say, the electrons aren't in the same orbital and they have opposite spins. Okay. Now here I'm kind of representing an electron going into a higher energy orbital. But things like oxygen, right, O2, right, oxygen molecule is native triplet, right, which is what causes it to be such an annoying reactive species for a number of reactions and a number of compounds and chemicals. The fact that it's this triple oxygen. Okay. But yeah, so the ground state of a molecule can be a triplet. It's not nearly as common as singlet, but you can have that. But you can have excited states that are these triplet states, which again, they're called triplet because each of these, so I have this dashed line here, each kind of configuration of electrons in some orbitals represented by these, arrows and over these horizontal lines, right? Each one of these things has the exact same energy. If you were to try to calculate, solve for the energy of each one of these configurations, they will have the exact same energy, okay? So they're all degenerate. So this spin configuration is triply degenerate, and that's why they're called triplet states, okay? So just kind of give you a background as to when I call something a singlet versus a triplet, what that's referring to, okay? And the key thing out of all of that, should I keep on using the arrow and I can't do that. The key thing out of all of that is that typically your ground state for most molecules is a singlet, and the excited state that you're going to excite into is going to be a singlet, okay? Because when you absorb light isn't really able to, at least at low enough intensities until you get the higher order effects, flip the spins of your electrons, okay? And so if you're in a single ground state, you're going to absorb light to get into a single excited state, okay? And once you're in that single excited state, that state can decay in a variety of ways, okay? So here is kind of a list of some of these different ways, right? Mainly kind of focus on things like fluorescence, intersystem crossing, phosphorescence, and internal conversion, okay? These are all kind of first order rates, okay? First order reactions, just like absorption is a first order process, right? And so these kind of first order processes, right, is what we'll focus on. And we'll focus on these because these happen in every molecule, okay? Some of these other things that occur down here that are second order reactions, right? Those might not occur in every system, every molecule. They can depend on kind of what are the relevant energy levels and how are they related to each other and things like that. So we won't really use that or talk about those, and we'll just focus on these first order processes, right? Where some molecule gets into an excited state. That excited state called S star here is metastable, right? It doesn't want to stay there, and it wants to go back down to the ground state. Now it can get there by fluorescing, right? Undergoing fluorescence. You can get down there by doing internal conversion, right? Where you right, release that energy through heat and kinetic energy and things like that, okay? Or you can do intersystem crossing, which forms a triplet state, and then that triplet state can do phosphorescence to form the singlet ground state again, okay? Now, often these two processes here are very slow because they involve flipping the electron spin, right? Involves going from a singlet to a triplet, right? Or a triplet to a singlet. This is a very slow process. Doesn't occur very often, and can take often very long time to do so. Okay. So I'll pause here real quick. Are there any questions so far about kind of just the general definitions of things, terms I'm using. Okay, again, it's given the different backgrounds of everybody and things like that. It's tough to know has everyone already seen some of this stuff? Do some of these terms, singlet, triplet, and other things make sense? And things like that. So I want to just kind of make sure there aren't any questions about any of this.
So I didn't understand very well what is a singlet. So I don't know if you could explain a little more, please.
A triplet?
A singlet.
Singlet. Yeah. So a singlet state is referring to a singlet electronic state. So it's it's referring whenever like you hear terms in papers, you hear, oh, this is a singlet, a doublet, triplet. That's referring to the type of electronic state that molecule is in, right? Whether it be its ground state or some excited state. And so singlets are formed through pairing up your electrons. So you have even number of up and down spins, and they're all paired up in orbitals, right? And it's called singlet again because there's only one way you can pair up your electrons, to form, say, the lowest energy state, right? I had this very simple example of, right? This would be like for the hydrogen molecule. This is like my sigma bonding orbital for the hydrogen molecule and my sigma antibonding orbital energies. Okay, right. That's what these energies represent, like sigma and sigma star, right, for the hydrogen molecule, right? There's only one way I can put my electrons together in the same orbital with opposite spin, right? And so this has one way of doing it. So it's singly degenerate, so it's called a singlet state. And again, this is going to occur when you have an even number of electrons. Okay, if you have odd number of electrons, you'll form what's called a doublet state. If you're dealing with radicals or things like that, I know Dr. Hudnall has lots of chemistry that he deals with that involve radicals and things, and so often, they can deal with these doublet states. But yeah, doublet state is when you just have one of these electrons and not both. Okay. And then, and so in most molecules, especially organics, are in singlet to ground states. Most molecules have singlet states like this, okay? And then you have excited states, and you're gonna have triplet and singlet excited states, and even higher order spins. But we'll talk about that. And then the thing is you can only, through the absorption or emission of light, you have to stay in the same type of spin state, whether it be singlet or triplet. Okay, you have to have extra things occurring to undergo this intersystem crossing or phosphorescence. These things require other steps or other interactions with your molecule, things like spin orbit coupling and other such things that I don't really want to get into, but really, if you have transition metals and things like that, then you can have this phosphorescence and intersystem crossing happening very rapidly. Okay, but if it's kind of pure organics, that it can take a very long time for those events to occur. Does that clarify at all kind of what I mean by a singlet and this S and S star and what that's referring to? It's referring to the electronic states of your molecule.
Okay, thank you.
All right. Often we care about asking kind of, right, in all of chemistry, right, we care about what is the yield of some reaction, right? And so here we care about what we'll call the quantum yield, which is still just a yield of a reaction, but it's related with, kind of things happening at the quantum level, if you will. And so, right, the yield of this reaction, this quantum yield, is related with the number of desired events, right, over the number of kind of reactants, right? Your reactant here is your light particles, your photons. How many of those are absorbed, right? If I absorb 100 photons, right, I've created 100 excited molecules, right? So that's my reactants, okay? right? And then the desired event could be fluorescence, could be intersystem crossing, right? Could be internal conversion. Okay, and I would need to count that in some way to determine how many times my desired event occurred over how many kind of reactants I had, right? Again, like the yields that we care about in chemistry, or how much product did you get divided by how much reactant did you start with, right? And so it's the same thing here with photochemistry, okay, in terms of the quantum yield, right? But instead of trying to measure the total number of events, okay, if I know the rate in which my event that I care about occurs, if I multiply that by some time interval, well, that will give me how many events happened, right? And the same thing is true for the absorption, right? If I know the rate of absorption and I multiply that by some time interval, then that will tell me how many absorption events occurred, right? And so this ratio, can simplify down to, instead of looking at the total number of events, just the rates in which these events are occurring. And so VI here is the rate in which the event I, fluorescence, phosphorescence, internal conversion, whatever you want it to be, occurs, right? And then I absorb is defined as the rate of absorption, okay? Right, I think I have it on this slide. So the rate of absorption is just defined, right, is right, I absorption is defined as that rate of absorption, right? How fast does your molecule absorb that light? Okay. And then again, then for these other reactions, right, the rate laws that we have are all going to be first order rate laws, first order kinetics, okay, for both fluorescence, intersystem crossing, and internal conversion. We won't worry about phosphorescence because that depends on concentration of the triplet, okay, which is just not something we're sorry, that we're worried about. Okay. And so, right, the rate of disappearance, right, how much does the concentration of S change as a function of time? Assuming, so here I'm assuming that I've done my absorption, I turned off my spectrometer, if you will, or whatever, right? I've turned off whatever thing I'm using to shoot light at my object. It's no longer absorbing, right? So this equation goes away, right? Because if I turn off the light, there's no light, then I can't absorb that light, and so this just never happens, right? So the question is what's kind of the dynamics of these three events that are occurring, right? These all three are first order reactions, and so you can just add up the rate constants and multiply that by the concentration of S star, and that will give you what is the change in the concentration as a function of time. And then that just forms our typical integrated rate law for first order kinetic problems, okay, which we'll also rewrite in this form here, where instead of using some of these rate constants, we'll use a term defined as tau naught, which is called the lifetime of that singlet excited state, okay, which happens by definition for this molecule to be 1 over kf plus 1 over k, 1 over kf plus KIC plus KIC. Okay. That's just what the lifetime is defined as. And this is something, so if you were to measure the concentration of your excited state as a function of time, you would get an exponential k, and you would be able to fit that exponential k to get what is the lifetime of the excited state. Questions? All right. Okay. Now, if you were to undergo constant illumination, okay, you would reach a point, right? So let's say you're just shining light continually on this molecule, right? That means it's continually absorbing that light to form an excited state. The excited state, its concentration is going to be increasing as a function of time until it reaches a point where there's so much excited state that that excited state's decaying fast enough to go back down to the ground state. And in that situation, you're going to reach some steady state of concentration of the excited state, and the total concentration of S star is going to be unchanged, right? Okay. Because again, the rate of formation is then dependent upon the concentration of S star, but as the concentration of S star increases, right, the rate of consumption of S star increases, right? Because its rate is literally dependent on concentration. Okay. And so eventually the concentration of my intermediate is going to get large enough that the sum of these three rates is going to equal the rate of absorption. Okay. And so, yeah, so we set that change of concentration of S equal to 0, say, okay, well, the rate of absorption under these steady state conditions has to equal this. Okay. Right. And so if we go back to our definition of fluorescence, okay, fluorescence was defined as the rate of fluorescence or the rate of absorption. Well, the rate of absorption can be rewritten in terms of S star and the sum of these rate constants. The rate of fluorescence, right, we just go back to this equation, right, the rate of fluorescence is just Kf times S star. Let's plug those in, right, and we get this simplified expression for the fluorescence yield, right, for this reaction. And this is this simple equation that's just dealing with ratios of rate constants. All has to do with the fact that we're talking about these parallel competing first order reactions. Now, all the reactions we are considering here are first order, so it ends up just things working out very nicely to get this type of an expression for the yield of that reaction, the quantum yield. Okay. So questions about how we got this fluorescence yield, anything again about rates of excited states before we continue on with it. All right. Okay. So let's talk some quenching. Okay. So this is an aspect of photochemistry and the kinetics within photochemistry that's used quite often. So I mean, in papers, you'll often see lifetimes of excited states reported and things like that. You'll say quantum yields of singlets and triplets and things of that nature. Okay. Right. I mean, these things are very important for depending on your application, right? If you're trying to design a photovoltaic device or a OLED or some light emitting diode or something like that, right? Quantum yields of certain of these processes, right, are very important, right? In an OLED, you want very high efficient fluorescence and phosphorescence, and you do not want very large intersystem crossing. Okay, or sorry, internal conversion. You don't want large internal conversion for OLEDs, right? But you want large fluorescence or phosphorescence. For photovoltaics, you don't want fluorescence or any of those things to occur. Really, you want a different process to occur to generate charges from that absorbed light and things like that, right? So controlling these things, understanding them, plays a key aspect in a variety of applications and areas of chemistry. Okay, and one other thing that often people look at and study are these quenching studies. Okay, and the reason we do this is because using these quenching studies, you can often get out rate constants very easily, and we'll see how in these quenching studies. And often these rate constants can tell us something important or interesting about what's going on in your system in terms of kind of what reactions, what's limiting the rate of reactions or other things like that. It can be even used to study the distance dependence within systems at a molecular level. Okay. And so what is quenching? How does it work? Okay. So the idea behind quenching is just you have some excited state in your molecule, right? And along comes some molecule that we're going to call the quencher, Q, that sucks out that excited state energy. Quenches, this excited state's, a flame, right? It quenches that flame. It burns it out, puts it back down to its boring old ground state, right? and takes down the energy itself. Now, in the quencher, that energy then quickly dissipates and goes away, and you just form the ground state quencher as well, right? And so effectively in this reaction, the quencher's concentration doesn't change. Okay? If it does, then it's not quite acting like, well, it can still quench your system, but if it doesn't dissipate that energy quickly, then the kinetics don't quite work out as simply as we potentially have here in certain aspects, okay? But anyways, okay. So the rate for this reaction is, right, the rate law is then just the quenching rate constant KQ. So imagine, right, I had written up over here, right, some KQ, right? That I have some rate constant for this reaction, KQ. Sorry, my mouse got stuck there. Right. So I have some KQ for this reaction. Okay. So imagine we have that, right? And so the rate constant is that rate constant. The rate is just the rate constant times the concentration of your reactants, which is Q times S. Okay. Often Q, as this is occurring, its concentration is relatively constant. Okay. And so this can be thought of as essentially just first order rate with respect to S star, and really first order total, because Q is often unchanging in its concentration as your reaction's going on, right? Because it shouldn't, right? The concentration of Q should remain constant because it's not, Q is not being altered by this reaction, okay? So basically all this does is it adds an extra equation to these sets of equations we had before, right? We had these three equations for the decay, right, of your system. And I just add one more equation for the decay, and that's that quenching rate, okay? And so all that does is just add an extra term here, okay? Right, where I have Kf plus KIC plus KISC, right? I basically have those terms still, but now I get this KQ times Q, right? As this extra term dealing with this quenching, okay, which will decrease the quantum yield of, say, your fluorescence, right? And will also decrease your lifetime. Right? The lifetime is then just a sum of all these rate constants, right? And includes the concentration of your quencher times KQ, okay? So the quencher will definitely reduce your lifetime in your system, as well as, say, your fluorescence yield, right? And if we use the definition of the fluorescence yield without the quencher and the fluorescence yield with the quencher and take a ratio of these things, okay, right, so phi F divided by phi FQ, right, the fluorescence yield with the quencher, okay, right, dividing by phi FQ is the same thing as taking the reciprocal of the fraction and multiplying it, okay, so that's why I have the reciprocal here, right, and I'm multiplying it together, right? And we see here the KFs cancel, right? In this, right, KF cancel, okay? In this term, right, I can, right, separate the numerator into this, which is just, you know, same thing on top and bottom. So that just simplifies down to 1, right? And then KQ times Q divided by this term here, which happens to just equal the native lifetime, right? And so often for these Stern-Volmer prods, these quenching problems, right, you'll measure the lifetime without any quencher, okay? And then you just measure, say, the fluorescence yield or the lifetime. Another way you can write this is through the lifetime, right? And measure that as your reaction's going on and things like that, and as a function of Q in order to get out what this quenching rate constant is. And here, right, so this is a Stern-Volmer equation, as they call it. This is just another form of it, okay? The derivation is kind of just given here, right? This is defined as tau naught, this is defined as tau. It's got these things here, and I can plug it in to get, you know, this relationship with lifetimes and the quenching constant, or the quenching concentration and the quenching rate constant, right? or you could stick with this fluorescence yield, right? So it just depends on what you're able to measure, right, in lab and things like that as to which version of this equation you want to do. But both of these are valid. Okay, the red highlighted version of this equation at top, labeled the Stern-Volmer equation. So questions about this? Questions about quenching, how that's affecting things, affecting our rates, our rate confidence, and other such things. All right, right, and so this alternate version of the Stern-Volmer equation, right? If you were to plot 1 over the lifetime plus, or sorry, versus concentration of Q, right? You'd get a straight line with the slope as KQ, and then the y-intercept is 1 over the lifetime of the unquenched species. Okay. So again, this is something that's done very often. Or at least was, it still is done often in some labs, right? And again, it's done to get this quenching rate constant, which there's a lot of things you can learn from by knowing kind of the value of that quenching rate constant and changing up what your quencher is and doing other things. And so there's a lot of underlying chemistry that you can learn by knowing the value of KQ. All right. So questions about that, and then you're welcome to think over those while you also look over this question. Where do we have bipyridine forms a complex with ruthenium? That ruthenium bipyridine complex, right, can get quenched by iron in solution, okay? And you're given kind of data of concentration of iron in millimolar versus the lifetime of your bipyridine ruthenium complex under these different concentrations of quenching, right? So the question is, right, what is the quenching rate constant for this reaction? And so what would you want to do with this data, right, to find KQ? Or what might you want to plot in order to find KQ?
You plot concentration versus 1 over the lifetime.
Yes, right. So, right, if you look on the previous slide here, this alternate form of the Stern-Volmer equation, right, and you plot 1 over the lifetime versus that concentration, that'll give you a straight line where the slope of that line is KQ. Okay. So all you need to do for this data is calculate 1 over that lifetime, right, at these different concentrations. And then, right, you would plot it and fit it to get the slope and whatever, right? But here, I'm just going to take the difference between these last 2 points to calculate the slope, right? And I get, 0.0028 millimolar, inverse millimolar, inverse microseconds, okay? Right, and the units of K here, inverse molar, inverse seconds, because this KQ comes from the rate equation, right? That's overall second order, right? It's first order in Q, first order in S, overall second order. So an overall second order rate law is going to have this units, if you will, for the rate constant. All right. So questions about things. I think, that's a lot of different kind of topics and different things to go over and discuss today. On top of everything we talked about with kinetics on Monday, that I don't think it's worth in this last 10 minutes to try to fit in discussion on polymerization or going into detail about these inhibitors or other things like that. Okay. But again, I'm happy to answer any questions people might have on any of these topics related with kinetics or anything, I guess, in general, right? I'll say, right, again, on Monday, you'll have that first exam, right? It's 60 minutes. You'll be taking it you know, sort of via Canvas, right, as just a reminder how that's going to work. And I'll send an announcement as well to remind you, right? But the idea is you'll need to log into Zoom, okay? Right. And when you log into Zoom, you know, you have to have your camera on. It has to show kind of your work area or things like that, right? Is the idea to verify, right, that you don't have extra things going on, people aren't helping you, or whatever the case may be, right? And then, right, and then you'll go on Canvas, you'll open up the exam on Canvas, and then you'll write out your answers on whatever notepad, piece of paper you got going on, right? And then you will scan those answers and upload them to Canvas, to the quiz that will be created, that is created for the exam, right? And then that's what will get graded. Okay. I'll note here, so a number of people, when they submitted their homework to me, and that's fine for this first homework and everything, but a lot of people, when they submitted it, they submitted a lot of images, right? So they just took a picture, say probably with your phone, right, of these things, and submitted those images. And so, you know, I have like, you know, a bunch of images per student and things like that, which is okay. But I really encourage people for here on out, for other homeworks for the exam, to you know, assuming you use a smartphone to take a picture of these things, right, to download what's called the Adobe Scan app. Okay, here I can stop sharing my screen here, right? Oh crap, it's already trying to scan, right? So I already have it open trying to scan. If I had some piece of paper in front of it, right? So on your phone, it goes like it's trying to take a picture, right? You know, I don't know if you can kind of see, but it takes, you know, picture. I'm trying to show it, right? As a picture, has these little dots that you can then use to define where the edges are on the paper, right? And you can move those around and whatnot, and then you can click continue and take more pictures, right? If you click continue, and let's say you're done taking pictures, then you can just click on the bottom on the images, and it will, you can't really see it because of the lighting on my phone and things like that, but right, it then pulls up this thing, you know, like what you have, and you can go through the pages, you can rotate them, you can crop them, you can edit them however you want, okay? And then you can just, on the very top, it just says save PDF, and it saves it as a PDF, and then you can immediately, you know, share that PDF, and you can share a copy of it and email it to yourself if you want to, or whatever the case may be, right? And so it's very simple to use. It's completely free. You can create as many PDFs as you want, and then it will make it a lot easier, because then it will create just one file for your work instead of multiple files for your work, right? And it will, again, make them as a PDF. This is a little bit easier to open, manipulate, and comment on if Kelly wants to kind of do that, right? She wants to edit a PDF, right, using Adobe Acrobat and make comments or write something or highlight something, right, and give that back to you, right? She'd be able to do that with a PDF more so than with a JPEG. I guess you could use Illustrator or something, but it's just, yeah. So again, I really encourage downloading that Adobe Scan app. If you don't have a smartphone, then I guess, you know, that's fine. You know, I don't know if everyone does. You know, it took me a while to eventually get one myself. But yeah, so if you have a smartphone, I suggest you do that, just because it will make it easier for you, because then you just upload one file, and it will make it easier for myself and or Kelly.
Actually, downloaded that earlier today just to test it out. And if you guys don't have it, I'd encourage you to just play around with it a little bit, because there is one setting where it kind of automatically tries to take photos like you were showing earlier, Shane.
Yeah.
But you can turn that off to make it manual. So it's not trying to take photos all the time. But yeah, definitely try to do that before the exam, because I'd hate for you to need 2 or 3 minutes at the very end trying to scramble. Don't want this to be anxiety producing. So
yeah. So yeah. You know, there's another homework. Actually, I don't know when that I said the kinetic homework was when I had that due date. I should look that up. So, you know, I added some extra kinetic questions for homework just so you had something to go off of for the exam. And I don't know if I had when did I have that due? I'm going to go right to under assignments. Yeah, so that's due kind of the same day as the exam. So you can always practice by scanning that homework and uploading that before the exam. Yeah. I guess, let me ask you this. I realize now that because the homework's due the same day as the exam, I wouldn't want to put up the solutions before then. Would people like, I don't know if anyone's looked at that kinetics homework, has started it. I can change the date in which that's due or the time so that you can look at the answers. Now, again, as I mentioned in the announcements, the homework question that will appear on the exam won't be from this homework, from this kinetics one, but it does have problems that are relevant to potential questions that could appear on the exam, right? And so if you want to be able to see those answers, you know, ahead of time, right, and kind of check your work versus the answers or things like that, then I can always, change that due date so then, I can post the answers earlier. So I don't know if people would like me to do that, make it due earlier, like Sunday evening or something, then you can like study it Monday morning, I guess, or something like that. Yeah. So like, is Sunday evening a good time to where it's not like, hey, the homework's due tomorrow, but it also gives you at least some amount of time, or does anyone else have a different suggestion besides basically Sunday evening?
I would say a Friday evening is fine. Or I'll go with the others one too.
Yeah. I don't know. I can try making let's see here. I can do a poll real quick. Question. Susan, I still have a minute or two, right?
While you're putting that together, Shane, another thought that I just had was that on Monday, I guess folks will be using my Zoom account, which I'm still kind of getting set up. There's a lot of paperwork and stuff to get hired. So I wonder if it makes sense to try to join a little bit early just to make sure you're able to get on and have the right link. I'll put an announcement in Canvas with the link. And I think right now, Shane, you don't use any validation or passcodes or anything.
I mean, it does have a passcode if you don't use the link. So the link just automatically like enters a passcode and things like that. But if you just enter in like the session ID, you also have to enter a passcode. Which I guess I never put that up there. I guess I just assume people click on the link. Or did I put it on? Let me see. Let me go to the home page. I thought I put that. Yeah, so the passcode's there, right? So there's a meeting ID and then there's a passcode 6989992 that was just like whatever generated, right? So yeah, so there's the link and a passcode that also gets made for these things automatically. But yeah, but that is a good reminder, right? Kelly's going to be in charge of the Zoom sessions from now on and not me. So she'll need to be the host and things like that. So that link to Zoom, Kelly will either email it out to you or update it on Canvas or something like that. After today, I'm going to just remove my link just so people don't end up getting confused and accidentally going to the wrong spot, right? But yeah, so let me see here.
And I realize it's a lot of stuff changing right before the exam. So happy to set up another call where we just practice getting on. I want to make sure that I know how to use Zoom the right way as well with all of you. But I'll let you answer this poll first.
Yeah. So yeah, so we'll just do a poll here and just go with majority rules. If there's a tie, then I don't know what I'm gonna do. Oh crap, it's a one more person like Kelly or myself. There is a tie. Oh no. Got a tie Saturday and Sunday.
Maybe make a new poll with just those two.
Let me, I'll make an executive decision here. Let me just look at, I just want to glance at the assignment just to decide myself. I think I tried to make it a relatively short assignment, so, but I want to see how short. Yeah, there's 6 questions. Let's do Saturday. We'll split the difference. Since one person said Friday, it's kind of halfway through. You know, Saturday's in between Sunday, so maybe the Friday person will want Saturday anyway. So I'm going to split the difference. I'm going to change that due date to Saturday evening, and then have the answers posted. I think I can do like a time reveal on the answers or something like that. But yeah, have the answers posted right after that the assignment is due. Okay, and so then you can go ahead and start studying that on Sunday as well.
Has everyone taken at least one exam online since everything? I see some shaking and nodding. Okay. I've never proctored an exam online, so I think I am gonna probably have one other person who has more experience join, just to, because I want to make sure everything goes very smoothly, but there's only a few of us, so hopefully if there are some kinks, it'll be quick to resolve.
Yeah. Typically what I like to do for online exams is I'll recommend people make sure you're showing up at least 10 to 15 minutes before the class time to try to work out any of those kinks. Make sure everything, you're able to log into Zoom and you got everything set up right. Since we're giving you a note sheet, so Kelly can take a look at the note sheet that you have, right? Or hey, if you want to practice this Adobe Scan PDF, right? Try making a scan of it, right? And maybe emailing it to Kelly and say, hey, is this fine or whatever, right? Again, my criteria on the note sheet, or you can email it to me, I guess, since I was the one who kind of set up the criteria, right? Right. My criteria was just, you can have, all these different equations that we've kind of presented, right? Write out what does the steady state approximation mean, the Stern-Volmer equation, things like that, right? But I obviously, since I said there's a question from the homework on the exam, I do not want to see people write out the homework questions and their answers on that sheet, right? So nothing like that, right? No writing example problems and answers to the example problems on your note sheet, right? The note sheets all just going to be, just equations, definitions, things like that. Okay, and you'll be getting like constants and things like that, so you don't have to write them down. If you want to, that's fine, but you don't need to write down the constants, or you shouldn't need to, right? And such. But yeah, that's the type of stuff on your note sheet. Again, not example problems and answers to them and things like that. So you can make there are some, like I have like on the exam, there's kind of some constants, 1 or 2 equations, but I decided I just didn't want to make. Yeah, I decided, especially because of the changes that we're doing all of a sudden, suddenly and things like that, I didn't want to make people have to memorize a bunch of crap and things like that. So, so I don't have a note sheet for this. For the other exams, I don't think you'll necessarily need a note sheet, and because I think a lot of the things would be given that typically you'd need, because in quantum mechanics and things, it's just thermodynamics. There's a lot of random equations, to be honest, so that's why I'm kind of letting you have it. But so you might not have one in the future exams, because I normally don't do it. but I'm just kind of making an exception for this one exam because of all the changes that have kind of happened. So, but yeah, again, there will be some constants, equations, and other things given to you on the exam. But yeah, if you want to write out, you know, a bunch of the Stern-Volmer equation, that's not on there. So if you want to write that out, write it out. You know, what does this mean? What is that? What is tau? What is tau naught? What is blah blah blah? Write that stuff out, and that's fine. All right. Other comments, questions, concerns? Okay. So yeah, like I said, I'll update the homework to be due Saturday. Okay. It's only 6 problems. It should hopefully not take too much time. Okay. And yeah, if you have questions, you know, on kind of the topics and stuff like that, you're welcome to email me about the class. Email me or email Kelly. And as things are going, you know, I'll still be, you know, in communication here and there with Kelly about, you know, things or whatever, just because probably there's something I forgot to pass off to her that, you know, she might want or use or something like that, you know, type of thing. So, so yeah, so just don't hesitate to contact me if you have questions and things of that nature. Okay.
So I have a question about the exam.
Yep.
So I didn't understand if we are going to answer on Canvas and then we are going to send like the PDF of our answers.
No, so something like, say, the homework, right? There's a homework PDF file uploaded, right? So there's going to be an exam PDF file uploaded that you'll be able to open on Canvas through so on Canvas you can make it to where people can only open a file through a link, and so you'll have like a quiz or an assignment that's only available to you during the exam time window, and in that assignment will be a link to the exam, which will be a PDF, right? And so you'll be able to open that PDF on Canvas. You know, if you have a printer and want to print it out, then you could print it out. But you'll just write your answers on a piece of paper with pen or pencil, and then those written answers you will then upload to Canvas. And again, I very much recommend using the Adobe Scan app to do that, because it's very simple, very easy to use, and it's free. And so yeah, so that's how that will work, right? You don't have to rewrite the question. I guess for me personally, I don't feel like you need to rewrite the questions. I know what the questions are, right? So just make sure you are clear and like, this is question 1, this is part A, this is part B, and things like that, right? But you don't have to rewrite everything from the question if you don't want to. That's more than fine, you know. So you don't have to take that time to rewrite everything. Okay. Other questions?
This is all good because I had similar questions too.
Yeah, and Kelly, if you want to talk to me afterwards or something about some other things, you know, maybe I'm always happy to chat. So, but you know, I'm saddened to not be able to do quantum mechanics and all that wonderful stuff with you guys. You know, as sort of a spur of the moment thing. I'm very grateful for Kelly to be able to come on and take over for me. You're in very capable hands. You're very knowledgeable and capable of teaching this course and instructing everything. And you know, and again, I'm still available via email and things like that. I can still set up a Zoom call, chat with you if you have questions or anything else like that. But otherwise, good luck with everything. I will grade this last homework I have, and I haven't finished grading it, but I'll grade it and post the grades soon. But the answers are already posted, and you know, you have your homework, so you can always just check your answers versus the answer key that's posted as well. Okay. All right. Good luck, everyone.